There are a number of grand questions we can ask about the universe that cut right to the very core of what reality actually is, and were some of the biggest head-scratchers for all of human history. Questions like, what is the universe? How big is it? And was it eternal, or did it spring into existence? And if so, when? Used to be some of the greatest philosophical mysteries, and yet the last 100 years have provided firm, scientific answers. But why, of all the ways there are to measure time and distance, do we use such an Earth-centric set of units like years and light years? Isn't there a better, more objective, more universal way to do it? There are really only two ways here on Earth to make sense of the concept of the passage of time, and both make use of the regular recurrence of phenomena that are essential to not only human activity, but all biological activity. On shorter time scales, we have the concept of days, which are important for a number of reasons. They mark sunrise and sunset. They correspond to, roughly, a single complete rotation of Earth about its axis. They correspond to the period where most plants and animals experience both activity and dormancy, all followed by a repeat of all of these phenomena, and more on the next day. Each year, with very little variation, the cycles of the previous year once again repeat themselves. Some 4 billion years ago, a day on planet Earth only lasted 6 to 8 hours, and there were over 1,000 days in a year. Even with all of the complex astrophysics taking place in our solar system, then, it's apparent that the duration of a year is probably the most stable, large-scale feature that we could use to anchor our timekeeping to our planet. Since the speed of light is a known and measurable constant, a light year then arises as a derived unit of distance, and also only changes by very little over time. It's consistent over billions of years to the 99.98% level. The other major definition that we sometimes use is also, albeit indirectly, based on the definition of Earth orbiting the Sun to make up a year, the parsec. Instead of being based on time alone, it's based on astronomical angles and trigonometry. As the Earth orbits around the Sun, the apparent positions of unmoving stars, relative to one another, will appear to change relative to one another, in the same way that if you open only one eye and then switch eyes, the closer objects will appear to shift relative to the more distant background objects. In astronomy, we call this phenomenon parallax. And instead of the distance between two typical human eyes, we use the maximum distance between Earth's position relative to the Sun, the diameter of its orbit, or about 300,000 kilometers. But why would we tie our definition of time, which extends to the whole universe, to the arbitrary motion of one planet in one galaxy around its parent star? It's not objective, it's not absolute, and it's not useful beyond our own Earth-centric interests. Neither days nor years are universally applicable as measures of time, and neither light years nor parsecs, or the associated quantities like kiloparsecs, megaparsecs, or gigaparsecs, are universally applicable as measures of distance. There are, interestingly enough, ways to define time that are based in more objective, physical measures, and they don't suffer from the same drawbacks that using an Earth-centric definition do. But there are some pretty good reasons for us not to use those measures of time either, as each one comes with its own set of both pros and cons, if you were to make an argument either for or against its use. Here are some options to consider, and you can decide for yourself whether you like it better or worse than the current year-based and Earth-based system of time that we've adopted for ourselves. You might want then to consider the Planck time. If we take three of the most fundamental, measurable constants of nature, the universal gravitational constant, the speed of light, and the quantum, the reduced Planck's constant, then it's possible to combine them in such a way to give a fundamental unit of time. Although this corresponds to an interesting scale, the scale at which the laws of physics break down, because a quantum fluctuation on this scale wouldn't make a particle-antiparticle pair, but rather a black hole. The problem is that there are no physical processes corresponding to this timescale. It's simply mind-bogglingly small, and using it would mean we would need astronomically large numbers of the Planck time to describe even subatomic processes. The top quark, for example, the shortest-lived subatomic particle presently known, would have a decay time of about 10 power 18 Planck times. A year would be more like 10 power 51 Planck times. There's nothing wrong with this choice, but it sure doesn't lend itself to being intuitive. Here's a fun, and possibly uncomfortable, fact for you. All definitions of time, mass, and distance are completely arbitrary. There's nothing significant about a second, a gram kilogram, or a meter. We simply have chosen these values to be the standards we use in our daily lives. What we do have, however, are ways to relate any one of these chosen quantities to another through the same three fundamental constants. If you make a definition for time or distance, for example, the speed of light will give you the other. So why not just choose a particular atomic transition, where an electron drops from one energy level to another and emits light of a very specific frequency and wavelength to define time and distance? Frequency is just an inverse time, so you can derive a unit of time by measuring the time it takes one wavelength of that light to go past, and you can define distance by the length of one wavelength. This is how atomic clocks work, and this is the process we use to arrive at definitions for the second and the meter. But again, this is an arbitrary definition, and most transitions are too fast, with too small of a time interval, to be of practical, everyday use. For instance, the modern definition of the second is that it's the time it takes for a photon emitted by the hyperfine structure of one cesium-133 atom to undergo a little over 9 billion wavelengths in a vacuum. So, don't like years or light years. Again, however, you wind up with astronomically large numbers for all but the fastest subatomic processes, which is a little cumbersome for most of us. What if we went in the other direction, and instead of using smaller quantities that come from quantum properties, we went up to cosmic scales? The universe, for example, expands at a specific rate. The expansion rate of the universe, frequently known as either the Hubble parameter or the Hubble constant. Although we normally write it as a speed per unit distance, like 71 kilometers per second, the speed, per megaparsec, the unit distance. All of a sudden, we could work with distance scales and time scales comparable to truly cosmic ones. Unfortunately, there's a big problem with doing precisely this. The Hubble constant isn't a constant with time, but drops continuously and in a complex fashion, depending on the relative energy densities of all the different components of the universe as the universe ages. It's an interesting idea, but we'd have to redefine distances and times for every observer in the universe, dependent upon how much time has passed for them since the start of the hot Big Bang. You might find yourself frustrated at how each of our attempts thus far to come up with a better definition of time has only led to a worse outcome for cosmic scales. But there's one possibility worth considering: the most common quantum transition in the whole universe. You see, whenever you form neutral hydrogen, it forms as an electron binds to the atomic nucleus, which is almost always just a single bare proton. When the electron reaches the ground state, there are two possibilities for how it will be configured relative to the proton. In the astronomical literature, you're likely to encounter times measured in some number of years, and distances measured in either astronomical units, parsecs, kiloparsecs, megaparsecs, or gigaparsecs, depending on whether we're talking about solar system, stellar, galactic, intergalactic, or cosmic distance scales. But because as humans, we understand the concept of a year fairly intuitively well, we simply multiply by the speed of light to get a distance, light years, and go from there. It's not the only option, but it's the most popular one so far. Perhaps in the far future, humanity will no longer be tethered to Earth, and when we move beyond our home world, we may at last move beyond these Earth-centric units as well. Thank you so much for watching. See you soon again in the next video. Until then, as always, keep looking up and dream big, and good night.